I really like this question. It's a really nice one. It's quite a good one for just sort of trying a bit of physics, okay, and applying some of the stuff you've learned in the course to your paper 1B. We've got this metal strip which is doing SHM, okay, and it's oscillating, it's drawing as the car moves down the ramp, okay, so it's making this trace, if you like. Okay, so we're going to look at that trace just now, and we're going to notice a few things here. Okay, and again, let me bring this over. All right, here we go. So we've got the pen displaced from equilibrium, and the car is then released at the same time. We know the frequency of the pen's oscillation. And what you'll notice here is I've sort of started drawing on here. We started here, and we're going 1, 2, 3 waves. Okay, that's important because we know the time for each wave is the same each time. All right, and then we also know the distance that's travelled here. We know that we're going 1, 2, 3, 4, 5, 6, 7 chunks of 2 centimetres. And so in other words, we're travelling a distance of 14 centimetres. This is going to be super important when we're doing our analysis. So we're doing 3 time periods and 14 centimetres. Let's have a look at why those are important. Okay, and we'll, oops, having trouble moving my screen, apologies. Okay, first thing to do is to remember that thing I said there, the time is 3 periods, okay, and 1 period is 1 over f. So therefore, if we take our 3 periods, that's going to give me 3 over f, 3 over 6.3, and it's going to give me 0.476 seconds. That's to 3 significant figures. You could do it to 2 significant figures here if you like as well. Okay, we're then going to use some suvat to do the acceleration of the cart. Okay, we're going to use the fact that s equals ut plus half at squared. We've calculated t, we know we began at rest, and we know the distance we travelled. And so I'm going to say 14 centimetres is equal to my 0, that's from 0 speed at the beginning, plus a half at squared. Okay, I'm going to rearrange that, so I've got a equal to 2 times 14 over 0.476. This gives me 123. Now this is where the units come in. Okay, I've kept this in centimetres because that's what I wanted to do. It doesn't say that I have to use any particular units, so but I have to make sure I write it down. So centimetres to the centimetres per second squared. Okay, you can also write this in meters per second squared, and that's just by dividing by 100 to go from centimetres to meters. That's 1.23 meters per second squared. Okay, so it can be either answer here. Now, one thing I was wondering here is what would happen if you just have no idea what to do. I would just write down the units, okay? There's no sort of harm in doing so, and it shows that you understand what the units should be. Now, last bit here, okay? We know that the ramp is inclined at an angle of 8 degrees, and so you're being asked to discuss how your value compares with the component of g that acts down the slope. Now, those of you who remember, a is equal to g sine theta. Okay, that means we've got a component acting down the slope, 9.8 times sine of 8, which is 1.36. And there's a difference here of about 10%, 0.13 between our two values. Now, obviously you've got a different value between the two here. Why are they different? Well, in our equation, we are not thinking about friction. Okay, this thing is traveling down the slope. G is not the only force acting on it. Actually, we've got a smaller acceleration, which means that we've not got the right value. It's not big enough, if you like. It's being reduced. Why is it being reduced? Well, that's because friction is acting down the slope. Up the slope, and stopping this from hitting the value that it should do. Again, this is a case where you're you're trying to evaluate the experiment via comparison to another value, and in this case, it's a value you have to calculate from your knowledge of mechanics. A really nice question.